So now I'm going to do a walkthrough of the machine. Let's start kind of looking at it from behind. And the thing that you see, the big black cylinder you see, is a 488 air-cooled laser. Right now we're running this red coherent Ooops. The air-cooled is blue 488. The red is what we normally use, and we just lift that out of there, and the blue is then automatically aligned. It stays aligned. The next thing that you see is a filter box. Nothing fancy about it. It's old-fashioned off of some older light scattering machine that we inherited. This is the input lens, L1. You can see that it has XYZ, and it also has tilt and yaw. The lens is plano-convex, and the curved side goes towards the laser. That is the correct thing to do. The sample is in there, and we look down through the side slit here to see the bright scattering from the sample. It's quite bright because it's a latex. There's a shroud here. It's a little plastic shroud that just lifts right out if you like it to. And actually the machine works perfectly fine for most applications without the shroud on. Because this lens here, this is the lens L2. The L2 lens is selected to have a focal length equal to about that distance, so that any parallel room light gets focused to a point and crashes off on this pinhole back here. So these are the pinholes, and then up here are the apertures. These are easily seen, all labeled with their dimensions in microns. Hopefully I can get this out without dropping it. And inside there are little pinholes and apertures. Sorry, this is the front, so this is apertures, and we just click them. It is possible in this system to take this sphere, this cylinder here, which contains the apertures, and move it to the back. You can swap them, and you might do that in cases where you have number fluctuations. To increase the volume that you detect, you would put the larger optics in the back. The back sort of determines the volume, and the front sort of determines, in concert with the back, the coherence. Alright, so then in this system here, I'll put that back together. There's a mirror, and the mirror, when it's pointed up, sends the light to an ocular, and you see exactly in that ocular what you see, what the detector will see. And you can drop the mirror, and now the light will go straight through to the detector. And when it's up like this, it goes here, and there's a mirror that brings it up to you, and you see exactly what the detector would have seen. We'll do a real quick experiment by popping in some reasonable slits. I gotta do this quick because I see that we have a battery issue here, and I don't know what's going to happen. We better turn on some electronics here in terms of making a measurement. We need those. This is our old and marvelous Pacific Precision Instruments photometer. Normally, and we'll see if I move the mirror down, I suppose we'll see some intensity come on. There we do, tons of intensity. So we will see if that's too much, but it's not going to hurt anything. We'll delete some by putting in those filters that you saw earlier, and there's a nice safe level. That's probably fine. That's pretty good. And we'll just do a measurement here by clicking the correlator on. I think it's button F2. And it's ALD correlators, and they scale for a bit, and there you go. And then taking a measurement here with modest coherence. A lot of people ask, why does the signal droop at the left? That's due to photodetector system dead time. This isn't the fastest system. You don't have to look at that if you don't want to. You can usually get rid of that. I'll get rid of this, I think, in one of these. There we go. So there's the standard Lin log time system, and over here you're seeing the intensity trace, and these are just random fluctuations that are really supposed to be there. This isn't dust. And after that, it's just a matter of analyzing.